Okay, this is injectors, October 2020. With reference to four-stroke engines, explain the effects of each of the following: advanced fuel injection, retarded fuel injection, and low compression pressure. Low compression pressure. Okay, advanced fuel injection. Explain the effects on a four-stroke engine. Effects of injection, timing, and pressure in four-stroke engines. That's a large title, isn't it? All right. Here's a breakdown of how injection timing and compression pressure affects four-stroke engines. Part A is advanced fuel injection. Injecting fuel early in the compression stroke can have both positive and negative effects. The positives are it improves power output. In some cases, advanced injection can allow for a longer ignition delay, leading to more complete burn and potentially higher power output. It can reduce NOx emissions. Early injection allows for more time for fuel-air mixing before combustion, potentially reducing peak combustion temperatures and thereby lowering NOx emissions. The negatives of advanced fuel injection are increased noise and knocking. Early injection can lead to pre-ignition, the fuel igniting before optimal timing, causing knocking and increased noise during operation. Potential power loss. Excessive advancement can result in incomplete combustion as the fuel and the air haven't fully mixed by the time the injection occurs, leading to power losses. Alright, so power losses and increased knocking are the negative effects. What are the effects of retarded fuel injection? So this is a little bit too late when you do the fuel injection. Delaying fuel injection timing towards the end of the compression stroke also has its advantages and disadvantages. The positives are reduced NOx emissions. Similar to the advanced injection with a slightly longer mixing time, retarded injection can contribute to lower peak combustion temperatures and potentially lower NOx emissions. It can also improve fuel economy. In some cases, retarded injection can improve fuel efficiency as the fuel burns closer to the expansion stroke, potentially utilizing more of the energy from the combustion process. So they're in a better place when it does actually ignite the cylinder. Negatives: reduced power output. Delayed injection leaves less time for complete combustion before the expansion stroke, potentially leading to decrease in power output. So improved fuel economy, reduced NOx emissions, but less power. All right. Increased hydrocarbon emissions. If the fuel injection is too late, there might be insufficient time for complete combustion, resulting in higher unburnt hydrocarbon emissions in the exhaust. So unburnt fuel being kicked out in the exhaust, which is contamination. Okay, great. Part B, that was retarded fuel injection. Part C is the effects of low compression pressure. Compression pressure is a crucial factor in the efficiency and performance of four-stroke engines. Here's how compression pressures affect the engine. Reduced power output. Lower compression pressures reduces the force pushing down on the piston and during the power stroke, leading to a significant decrease in the engine power output. Oh yeah, so we do this in just you do the power of the engine, and it works on the pressure. Higher pressure, more power. Increased fuel consumption due to lower efficiency of the combustion process. With lower compression, the engine needs to burn more fuel to achieve the same power output, resulting in higher fuel consumption. So it doesn't burn so well. All right, and incomplete combustion. In severe cases of low compression, there might be insufficient pressure and temperature for complete combustion, leading to an increased emission of unburned hydrocarbons and carbon monoxide. What, like if you don't actually ignite the fuel and you just push it out because you're at such low pressure on one of your cylinders? All right, finding the optimal balance. Engine manufacturers carefully design the injection timing and compression ratio to achieve a balance between power efficiency and emissions for a specific engine application. While adjustments might be possible in some cases, it's crucial to follow the manufacturer's recommendations, attain the optimal engine performance, and avoid potential damage. April 2022. Describe 5 defects which may occur with the main engine fuel injectors. Describe 5 defects which may occur with the main engine fuel injectors. Okay, diesel engine fuel injectors play a vital role in efficient combustion, and several defects can arise during their operation. This will affect the performance and potentially cause engine problems. Here are 5 of them. You can have sticking or leaking injector needle valve. Okay, I'm going to run through these 5 first of all. So you got sticking or leaking injector needle valve, Number 2 is blocked or worn nozzle orifices. Number 3 is internal leakage. Number 4, faulty solenoid valve. Number 5, a degraded spray pattern. Okay, so number 1, sticking or leaking injector needle valve. Description is wear or deposits on the needle valve can cause it to stick partially open or leak even when closed. Oh, so it doesn't properly close, it doesn't properly open. This disrupts the precise metering of the fuel intended by the injection system, so it squirts too much or too little. The symptoms are reduced engine power, pure fuel delivery, due to sticking or leaking valve can be noticeable decreased in, obviously if it's sticking, you're not going to get as much fuel, so you're going to get reduced engine power. Increased fuel consumption would be the opposite, right? So we're going to have like too much fuel being injected in there. So incomplete combustion caused by improper fuel metering can result in higher fuel consumption because you're squirting too much fuel into the engine. Black smoke emission. Excessive black smoke emission from the exhaust can indicate poor fuel atomization and incomplete combustion. Yeah, so if you're smoking a lot, I guess it's because you got unburnt fuel in the mix. Rough engine running. Uneven fuel delivery due to faulty injector can cause rough engine operation and vibrations. I suppose that would be on the different cylinders. If you got one of the cylinders that's not running properly, then you'd feel it because it would vibrate like a lot, because it wouldn't give out as much power as the rest of it. Blocked or worn nozzle orifices. As number 2, this is the problem. Number 2, describe 5 defects which may occur. So the first one was just sticking or leaking injector needle valves, and they gave a full description of it. Okay, great. Number 2 is blocked or worn nozzle orifices. Deposits from the fuel or wear on tiny orifices at the injector tip can restrict fuel flow and disrupt the spray pattern. So they're not spraying as they should be. They're all clumped together on one corner and one side, or not, under giving or over giving, like the ones above. This hinders proper atomization of the fuel, essentially for efficient air-fuel mixing and necessary for air-fuel mixing and combustion. The symptoms are similar to sticking or leaking valve. Blocked or worn orifices can lead to reduced power, increased fuel consumption, and black smoke emission, and rough running of the engine. So basically the same thing, very similar. This is worn orifices. The other one was sticking due to due to dirt, I suppose? Okay. Symptoms, internal leakage. Number 3 is internal leakage. Description is worn seals or internal components of an injector can allow internal leakage by bypassing the metering process. So that would be the valves, like the piston rings, I guess, something along those lines. No, injectors we're doing. All right. Number 3, worn seals or internal components of an injector can allow internal leakage by... This is a long one. It's too long. Okay, this is number 3 on the 5 defects which may occur with main engine fuel injectors. So number 3 is internal leakage. The description is worn seals or internal components within the injector can allow internal leakage, bypassing the metering process. So if your injectors are leaking oil all over the place, then they wouldn't be delivering the required amount. They should be, the fuel oil. Effect that this disrupts the intended fuel delivery and pressure within the injector. Oh yeah, so it affects the pressure as well. So it just wouldn't run right, I guess. The symptoms can be similar to those mentioned above, just like the other ones, but the severity might vary depending on the extent of the internal leakage. So it's the same symptoms each time. It doesn't say in the question we have to list the symptoms. It just says describe 5 defects. So we're describing them in detail, but the symptoms are always like black smoke, increased fuel consumption, reduced power output, which is always what we're saying, as reduced power, more emissions, more environmental damage, and rough running of the engine, so more maintenance on parts and damage due to maintenance, stuff like that. It's always the same. Faulty solenoid. Number 4 is faulty solenoid valve, if applicable. In electronically controlled injectors, a faulty solenoid valve might not properly actuate the needle valve. This disrupts the precise timing of the full injection process as controlled by the engine management system. So you got a default in the electrical control system. All right. Depending on the nature of the solenoid valve malfunction, it can lead to a couple of different issues. we can have engine starting issues. In severe cases, a faulty solenoid valve might prevent the injector from opening entirely, leading to difficulty starting the engine. Erratic engine operation. Improper injecting timing due to solenoid valve malfunction can cause erratic engine behavior and performance issues. So I guess your engine's going to be all over the place if your electronic system is malfunctioning. All right, number 5 is degraded spray pattern. Over time, wear on the injector nozzle or internal components can cause the fuel spray pattern to deteriorate. So it's not spraying evenly. It'll be spraying, like I said, off to one side. This can lead to an uneven fuel distribution within the cylinder, hindering optimal combustion. The symptoms might be similar to those previously mentioned. Yes, so always the same thing. Always increased fuel consumption, reduced power emissions, such as reduced power, increased fuel emissions, and potentially rough engine running. Yes, however, they might be less pronounced compared to the other problems, the other injector defaults. Defects. These injector defects highlight the importance of regular maintenance practices, including cleaning and replacing injectors as per the manufacturer's recommendations. This helps ensure optimal engine performance, prevent further damage to occurring, and maintain efficient and clean operation. The question is April 2022, 6A, is sketch a section through the nozzle of a fuel injector, labeling the main components, and explain what is meant by each of the following terms: atomization and penetration. Okay, I don't have a diagram just yet. I'll do one later. But for now, we're going to describe what should be in the diagram on the audio anyway. You can see it even if you're listening to the podcast, you're listening to the MP3. Fuel injector nozzle cross-section and main components. A typical diesel fuel injector nozzle has several key components arranged in a precise manner to achieve optimal fuel atomization and delivery. Here's a breakdown of a cross-section and the main components. Right, so the components are, there's like 6 of them, labeled up here. We've got body, and that's the main housing of the injector or nozzle, typically made from high pressure resistant steel. Sac, optional, a small chamber within the body that can hold a reservoir of fuel for improved injection response. Not all injectors have a sac design, so it's like a little mini reservoir on demand, or it should be like right next to the injector. Needle valve, a spring-loaded valve that controls the opening and closing of the injector, allowing pressurized fuel to flow through. That's the needle valve, a spring-loaded valve that controls the opening and closing of the injector, allowing pressurized fuel to flow through. So it injects the fuel. The nozzle seat, a precisely machined surface within the body that forms a tight seal with the needle. Oh, so it's where it sits. It's where the valves sit. Those are called seats, right? With the needle valve when closed. Spring, a spring that applies pressure to the needle valve, keeping it closed until the fuel pressure overcomes the spring force. So it's keeping it closed, basically. A spring holding the whole thing closed until you inject the fuel in, and it pushes open the valve. Nozzle tip, the tip of the injector where the fuel sits. It contains several tiny orifices, little holes arranged in a specific pattern, so that will cause a spray pattern into the piston. All right, fuel flow path. Because we're doing a diagram, we're explaining a diagram here. We're going to explain how the fuel goes through the injector. Fuel under high pressure enters the injector's body. When the pressure overcomes the spring force, the needle valve lifts, allowing fuel to flow through the sac, if it has one, and past the nozzle seat. The fuel exits the injector through tiny orifices at the tip, where it's broken up into a fine mist, which is called atomization, due to the high pressure and the design of the orifices. Yeah, so it just sprays into the engine, right? It goes through those stages. All right. Part B. This is part B of this question up here, which is explain what is meant by each of the following terms to do with fuel injectors, atomization and penetration. Okay, so explanation of terms. Atomization. Atomization in the context of fuel injection. Atomization refers to the process of breaking up a liquid fuel into a fine mist of tiny droplets. Yeah, so it's just spraying it, right? This is crucial for efficient combustion in diesel engine, and here's why. Okay, so there's a couple of points about why it's really crucial, why it's a good idea to do it well. It increases surface area, improved combustion efficiency, and controlled spray pattern. So we've got more control over how the engine's running, improved combustion efficiency, so it burns more because it has an increased surface area. Okay, I just think these are going to be the same thing, basically, but let's read them through. Increased surface area. By breaking the fuel into a fine mist, the total surface area of the fuel is significantly increased. This allows for better mixing with the air within the engine cylinder, promoting a more complete combustion. So it has a larger surface area, but also has more contact with the oxygen because it's all broken up into little droplets. Improved combustion efficiency. The better air-fuel mixing due to proper atomization leads to more efficient combustion, resulting in a higher power output and lower emissions. That's the same thing. You just said it twice. It didn't say how many we don't even have to say this. Atomization is a definition of atomization. So we got really 2 points on here, not 3. It's just to increase the surface area, and this therefore increases combustion efficiency because the fuel can burn better. And the controlled spray pattern. Design of the injector nozzle tip and orifice determines the spray pattern of the atomized fuel. This pattern ensures proper distribution of the fuel within the cylinder for optimal combustion throughout the power stroke. So I guess that could actually depend on the shape of the cylinder. It's going to be different. But basically wants to spray it out as much as possible over a nice even spread, but it would actually matter about the size or the shape, the size and the shape of the cylinder. Okay. The other thing they asked about was penetration. So penetration refers to the ability of the atomized fuel to travel a specific distance within the engine cylinder after injection. Here's its importance. Or like how far you blow it into the cylinder, right? So that would be penetration. And you blow it, I don't know, as much as possible, I guess. Let's see, not too much. I don't know. Couldn't really blow the thing up, could you? Reaching the combustion chamber. The fuel sprays needs to penetrate adequately to reach all the areas of the combustion chamber. Yeah, so as much as possible, ensuring proper mixing with air throughout the cylinder volume. Yeah, you want to get it in there to mix with the air as well. Optimum mixing. Good penetration allows for better air-fuel mixing, even in larger cylinders, promoting efficient combustion. Optimum mixing. Here's why it's important. You want it to get everywhere so it can mix. That is optimum mixing. Impact on power output. Of course, it'll increase the power output. Proper penetration helps to ensure all the injected fuel participates in the combustion process, leading to an optimal power output from the engine. I would have thought because the cylinder itself is hot, the more you can spray onto that, the more it's going to vaporize as well. But it should be fully vaporized before it even does that. But then I guess it would ignite in more than one place, and it ignite evenly throughout the whole cylinder. The design of the injector nozzle, particularly the size and arrangement of the orifice, plays a crucial role in achieving both proper atomization and desired penetration, characteristics for efficient fuel delivery and combustion. Yes, okay, that's a bit useless. But penetration is how far it gets sprayed into the cylinder. Okay, October 2021. With reference to Bosch or jerk type fuel injection systems, describe how the delivered quantity of fuel oil may be controlled, and explain the purpose of the delivery valve. Describe how the delivery quantity of fuel may be controlled, and explain the purpose of the delivery valve. All right, and that's with reference to Bosch or jerk type fuel injection pumps. Bosch or jerk type fuel injection pumps, fuel delivery control and delivery valve. Controlling the fuel delivery quantity. In the jerk type injection pumps, the delivered quantity of fuel oil is controlled by the interplay of 3 main components. There's a plunger and helical groove. The pump has a plunger that moves reciprocally with the barrel. The key element for fuel metering is a helical groove machined on the plunger's surface. Number 2 is a spill port and control rack. The barrel has a spill port that allows pressurized fuel to return to the suction side of the pump when uncovered. A control rack connected to the engine's governor or the electric control unit positions a sleeve around the plunger. Number 3, the operating principle. During the upward stroke of the plunger, fuel gets drawn into the pump chamber through an inlet port. As the plunger continues to move up, the helical groove on the surface progressively covers the spill port. The duration for which the spill port remains covered determines the amount of fuel trapped in the pump chamber for injection. The control rack position influences the orientation of the plunger and the helical groove relative to the spill port. By moving the rack, the governor or the electronic control unit can adjust the position of the helical groove, thereby controlling how long the spill port remains covered during the plunger's stroke. A shorter coverage time means less fuel trapped, corresponds to a lower fuel delivery. Conversely, a longer coverage time results in higher fuel delivery. Right, that was controlling fuel delivery quantity in Bosch and jerk type fuel injectors. I'm going to have to look it up, a diagram of that. Didn't really understand it. Part B is purpose of the delivery valve. The delivery valve is known as a discharge valve or pressure release valve, plays a crucial role in ensuring proper fuel injection pressure and preventing internal damage. Location. The delivery valve is typically located at the outlet of the pump chamber, directly connected to the high-pressure fuel line leading to the injectors. Its function. The valve remains closed by a spring until the pressure within the pump chamber exceeds a predetermined level. Oh, it's a blow-off valve, right? If it gets too big, it'll just explode. The purpose of a delivery valve. Why is it called delivery? Oh no, not quite a blow-off valve. It's not a safety valve. It's part of the injector, isn't it? But it works like that. The valve remains closed until by a spring until the pressure within the pump chamber exceeds a predetermined level. Oh, that's when it's ready to inject. Okay, operation. As the plunger moves upwards and the spill port closes, the fuel pressure within the chamber builds up, opening and injecting. Once the pressure reaches a set limit, the delivery valve opens, allowing a high-pressure fuel to flow through the line and reach the injectors for fluid injection. Safety function. The delivery valve acts as a safety mechanism by preventing excessive pressure buildup within the pump and fuel lines that could lead to component damage. So it is a safety mechanism. Closing and cycle repeat. After fuel injection occurs and the pressure drops, the delivery valve closes again, and the cycle repeats for the next injection event. Oh, okay. The delivery valve ensures that the fuel injection pump operates within design pressure range, delivering pressurized fuel to the injectors for efficient engine operation while safeguarding the system from excessive pressure. Okay, October 2020. With reference to scroll-type fuel injection pumps, describe how the delivery quantity of fuel may be varied. I suppose varied, yes. Explain the purpose of the delivery valve. Describe how fuel oil is prevented from spraying out if the high-pressure pump fails in service. Scroll-type fuel injection pump. Varying delivered fuel quantity. Unlike jerk-type pumps, scroll-type pumps achieve fuel metering through a fundamentally different mechanism. Here's how the delivered fuel quantity is varied. Scroll design. The core of the pump is a spiral-shaped scroll housed within a cylindrical body. In a rotor, and eccentrically positioned. What do you mean eccentrically? Let's get a picture of this thing. I reckon it's like a spiral inside of a housing. It spins, right? It's a scroll-type fuel injection pump. Let's Google it and see what it brings up. See. Scroll type. Oh, a bit more complicated. Scroll type fuel injection pump. Well, it's got a screw jack in it. Okay, yeah, so we Googled it and it literally is a spiral inside of a cylindrical body. Okay, and here's how the delivery fuel quantity is varied. And eccentrically positioned in a rotor, so they mean that there's a thing inside of it, right in the center of it. With rotors with blades rotates within the scroll. Fuel chambers. As the rotor rotates, crescent-shaped cavities are formed between the rotor blades and the scroll wall, acting as fuel chambers. So it just pushes the fuel through it, right? I reckon. Fuel metering principle. Fuel intake. During rotation, the expanding volume of the fuel chambers on the suction side draws fuel in through an inlet port. Part 2 is fuel trapping and compression. As the rotor continues to rotate, the scroll's shape progressively reduces the volume of the fuel chambers, trapping and compressing the fuel. And delivery valve and outlet port. A delivery valve is located at the outlet of the pump connected to the high pressure fuel line. During rotation, the expansion volume of the fuel chambers of the suction side draws fuel through the inlet port. As the rotator continues to rotate, the scroll's shape progressively reduces the volume of the fuel chambers, trapping and compressing the fuel. A delivery valve is located outside the pump, connected to the high pressure line. Then, when the pressure in the chamber exceeds the delivery valve's opening pressure, the valve opens, allowing the high pressure fuel to flow through the line to the injector. Oh, okay, now I get it. You build up the pressure and you squirt it in when it's ready. Okay. The amount of the fuel delivered per cycle is primarily determined by the geometry of the scroll and rotor. However, some designs might incorporate a bypass valve or a variable control sleeve to influence the filling and discharge process, allowing for limited adjustment of the delivery quantity. So the amount of fuel delivered per cycle is determined by the geometry, so the shape of the scroll and the rotor. You can't really change it. It's just the same. So the question's asking about explain the purpose of a delivery valve. That was part A, but it doesn't say how you control it. Describe how the Oh yes, it does. Describe how the delivery quantity of the fuel may be varied. Varying it. So it describes the shape of the rotor and how the rotor works, but it says you can't really change it. And that's weird, isn't it? Like, the amount of fuel delivered per cycle is primarily determined by the geometry and scroll of the rotor. So I suppose you can change the actual scroll on the rotor. However, some designs might incorporate a bypass valve or a variable control sleeve to influence the filling and discharge processes, allowing for limited adjustment of the delivered quantity. Maybe that's it. Maybe it's the a bypass valve or variable control sleeve to influence the delivered quantity. Part B is, what is the purpose of the delivery valve? Describe how the delivered quantity of fuel may be varied. Now, part B is explain the purpose of the delivery valve. The purpose of the delivery valve, similar to jerk type pumps, the delivery valve in the scroll type pumps serves a crucial purpose. Its location, its function, its operation, its opening and injection, its safety function, and its closing and cycle repeat are all important points. Let's look at them one by one. Location. The delivery valve is positioned at the outlet of the pump, separating the high pressure fuel section from the discharge line. Its function. The valve remains closed by a spring until the pressure within the pump chamber reaches a predetermined level. Operation. As the trapped fuel gets compressed during rotor rotation, the pressure within the chamber builds up. Opening and injection. Once the pressure reaches a set limit, the delivery valve opens, allowing high pressure fuel to flow through the line towards the injectors for fuel injection. Safety function. The delivery valve acts as a safety mechanism by preventing excessive pressure buildups within the pump and fuel lines that could lead to component damage. Closing and cycle repeat. After the fuel injection occurs, the pressure drops below the set point. The delivery valve closes again because of the springs, and the cycle repeats for the next injection event. All right. Part C is preventing fuel spray in case of high pressure pipe failure. And the question was asking, describe how fuel oil is prevented from spraying out if the high pressure pipe fails in service. Oh, so if it bursts apart, or if it comes loose, or if it sprays all over the place. How fuel is prevented from spraying out. So it must detect it and then stop the flow, right? Preventing fuel spray in case of high pressure pipe failure. Scroll type pumps typically incorporate a safety feature to prevent uncontrolled fuel spraying in case of high pressure pipe failures. Well, that's a good idea. Overflow valve or bypass port. Some designs might use an overflow valve or bypass port located within the pump housing. How does it work? Is in case of high pressure pipe rupture, the sudden pressure drop would cause the overflow valve to open or fuel to bypass an internal passage. The sudden pressure drop. Yeah, I can get that. The sudden pressure drop will cause the overflow valve to open. Okay, so just close another valve, basically. Or fuel to bypass an internal passage, so to direct the fuel a different way and not spraying all over the place. Fuel return. This allows the pressurized fuel to return back to the pump's low pressure side, the suction side, through the overflow or bypass mechanism. Preventing spray. By redirecting the fuel back to the low pressure side, the system prevents uncontrolled spraying of high pressure fuels, minimizing the risk of fire or injury. Okay, so I guess it's like a built-in safety feature, and it's like intrinsic to the actual shape of the thing itself, and it can just suck the fuel back into it rather than spraying it all over the place. Additional notes. Some scroll type pumps are generally simpler in design compared to jerk type pumps. Their flow rate is typically less sensitive to variations in engine speed compared to jerk pumps. However, the fuel metering capabilities might be less precise than those of jerk pumps. October 2023, question 1. With reference to combustion of fuel, explain each of the following terms: atomization, penetration, and compression ratio. We've done these before, so the atomization, penetration we did before, compression ratio we haven't talked about yet. State the factors which influence the terms explained in part A. Okay, so state the factors of the atomization, penetration, and compression ratio. We know what atomization is. That is basic spraying the fuel. Penetration is how deep it goes into the cylinder. Are you getting it all the way in there? Compression ratio, we do this in GS2 with mathematics, calculating it. Same thing on April 2022, same thing on February 2020. So quite a popular question on October 2018 as well. So common question. All right, Part A is the combustion terms explained. Let's explain what atomization, penetration, and compression ratio are. Atomization, the definition is, atomization refers to the process of breaking up a liquid fuel into a fine mist of tiny droplets. The importance of it is proper atomization increases the surface area of the fuel significantly. This allows for better mixing with the compressed air within the engine cylinder, promoting more complete and efficient combustion. The benefits are increased power output. Better air-fuel mixing leads to a more efficient combustion, resulting in higher power output from the engine, reduced emissions. Proper atomization contributes to lower emissions or pollutants like soot and nitrous oxide by ensuring complete combustion of the fuel. Also, you'd have less unburnt fuel being kicked out as well, so just like less oil in the exhaust gas in the exhausts. Part 2, question 2 was the penetration. Define penetration. Penetration refers to the ability of the atomized fuel to spray to travel a specific distance within the engine cylinder after injection. The fuel spray needs to penetrate adequately to reach all the areas of the combustion chamber, ensuring proper mixing with the air throughout the cylinder volume. Throughout the cylinder, yeah. The impact. Well, the benefits, I think it's trying to say, is efficient mixing. Good penetration allows for better air-fuel mixing even in larger cylinders, promoting efficient combustion. The power output. Proper penetration helps to ensure injected fuel particles in the combustion process, leading to optimal power output. Incomplete combustion. Insufficient penetration can lead to some fuel droplets not mixing well with the air, resulting in incomplete combustion and potentially higher emissions, so having fuel oil in your exhaust. Okay, compression ratio. So this is how much you squash the gas. It'll be between the swept and the swept stroke, and then the non-swept bit, the clearance part, the clearance volume. Okay, the compression ratio is a dimensionless parameter that compares the volume of the cylinder. Yeah, it's a ratio. So it's like 0.5 or 0.3 or something like that. Or you can write it as a percentage as well. You could turn it into a percentage, the compression ratio. You could say has a 200% compression rate. The compression ratio is a dimensionless parameter that compares the volume of the cylinder with the air-fuel mixture at the bottom of the intake stroke, that's the maximum volume, to the volume of the compressed air mixture at the top stroke. That's the minimum volume. So when you squash it, it's like how you're comparing the total volume of the cylinder to the cylinder after you've at the top of the stroke, because you're compressing it. So the importance. A higher compression ratio signifies a greater compression to air-fuel mixture, leading to higher temperatures and pressures within the cylinder. And as you've seen in JEST 2, we do those calculations, and you can get more power out of your engine if you run it at a higher pressure. Impact on combustion. Improved efficiency. Higher compression temperatures promote more efficient ignition and combustion of the fuel, leading to better fuel economy, so it burns better. Increased power output. The higher pressure in the cylinder during the power stroke translates to a greater force acting on the piston, resulting in increased power output. The trade-offs, like the negative effects, I suppose, while beneficial, excessively high compression ratios can lead to problems like engine knocking and the need for higher quality fuels to avoid pre-ignition. And you can also damage your engine if you do it too much, but working within safe limits. Part B is factors influencing the combustion. Oh, these are part B. What factors influence those three? The atomization, penetration, and the compression ratio. What factors affect it? For atomization, it is injector nozzle design, fuel injector pressure, and fuel properties, so the fuel itself. So it's the piece of equipment you've got, it's how you're using it with the fuel injection pressure, because you can adjust that, I suppose, maybe not, I didn't say you could. And then fuel properties, like the actual thing you're burning, the actual fuel oil you're burning. Oh, this is going to affect atomization, how well you can spray it out. Injector nozzle design. The size and arrangements of the orifices in the injector nozzle tip significantly influence how finely the fuel is atomized. Yeah, so it's the fitting you got on it. You could have the wrong head on it and it wouldn't atomize as well as you wanted it to. Fuel injector pressure. Higher injecting pressure generally leads to finer atomization due to the increased force of breaking up fuel droplets. So high pressure is good. Fuel properties. The viscosity and volatility, how much it burns, of how volatile it is, of the fuel can affect its atomization characteristics. Yeah, so how sticky your fuel is. If you've got some really heavy fuel oil, it's going to be much more difficult to atomize than some light stuff like octane or something really light. Like Formula 1 fuel would be the lightest, I would reckon. All right. Penetration. Injector nozzle design. The spray pattern and angle of the injector nozzle can influence how far the spray penetrates within the cylinder. Oh, this is penetration, so it's squirting it in. So of course, your design of your nozzle is going to affect how you spray it, and you're going to have different ones for different engines. Injecting timing. The timing of the fuel injection relative to the position piston can affect the available space for the spray to penetrate before combustion starts. Yes, you want to be spraying it into a large volume, not a small volume, so you want to wait until it's at bottom dead center or something like that. Or just before that. Higher engine speeds. Higher engine speeds can lead to turbulence within the cylinder, potentially affecting the penetration of the fuel spray. A bit of hydrodynamics, but aerodynamics inside of the engine. That's interesting. All right, turbulence. Number 3 was compression ratio. So what are the factors affecting compression ratio? Engine design, like how big the thing is, how the actual engine parts, the engine physical design, particularly the cylinder head and piston crown. Shape determines the maximum achievable compression ratio. Yep, I reckon that's about it, isn't it? It's just going to be the way the engine's built, and you're not going to be able to change that. Clearance volume, the volume remaining above the piston at top dead center of the compression stroke is called the clearance volume. A small clearance volume contributes to a higher compression ratio. So yes, you're going to squash the air, and if you've got a small space to squash it into, you're going to have a very high pressure. Fuel characteristics. The octane rating on the fuel determines its resistance to auto ignition. Higher compression ratios typically require fuels with higher octane ratings to avoid pre-ignition. Octane, that's because it's just based around the hydrocarbon octane, but it's nothing to do with actual octane. Well, as relative to octane, and how well it burns, or how easily it is to ignite it. That's what lead was used for, right? Leaded fuel, to stop it from just doing auto ignition. High compression ratio typically requires fuels with high octane ratings. That's it.